Imagine a robot hand that can pick up a delicate object with the same finesse as a human. That's the promise of RLDX-1, a new foundation model for robot hands. Arjun, this paper immediately grabs your attention with its bold claims, right?
It certainly does, Maya. The paper introduces RLDX-1 as a general-purpose robotic policy for dexterous manipulation. This isn't just about moving objects. It's about subtle, precise control that has historically been a huge challenge for robotics. The authors frame RLDX-1 as an evolution beyond current vision language action models, or VLAs. While VLAs excel at broad scene understanding and language-conditioned generalization, they often falter when complex physical interaction is required, like manipulating objects with high degrees of freedom.
So VLAs are great at seeing and understanding the world and then generating a general plan, but when it comes to the nitty-gritty of physically doing something complex, they hit a wall. What exactly are these broader functional capabilities that VLAs currently lack?
Precisely. The paper points to critical gaps such as motion awareness, long-term memory, and physical sensing. These are the nuances that allow a human to, say, feel the texture of an object or predict its movement, which VLAs typically miss. RLDX-1 tackles these limitations head-on with its core architecture, which they call the Multi-Stream Action Transformer, or MSAT. This architecture is designed to unify heterogeneous modalities by integrating them through modality-specific streams using a cross-modal joint self-attention mechanism.
Okay, heterogeneous modalities and modality-specific streams sounds very technical. Could you give us an analogy? Is it like a symphony conductor making sure each instrument section, the strings, the brass, plays its part but also listens to the others to create one cohesive piece of music?
That's a very apt analogy, Maya. The MSAT treats different sensory inputs like vision, touch, or proprioception as individual streams or sections. The cross-modal joint self-attention is the conductor, ensuring these distinct information types are processed collaboratively for a unified action plan.
The results really jump out. On Alex humanoid tasks, RLDX-1 achieves success rates of 86.8%. When you compare that to leading models like Pi 0.5 and GROOT N1.6, which are around 40%, that's a staggering difference. How significant is this gap in real-world scenarios?
This performance disparity is monumental, Maya. Moving from 40% to nearly 87% success means the difference between a robot failing more often than not and one that is reliably executing complex tasks. It unlocks a whole new class of applications for dexterous robots. This jump in capability is compelling, but the abstract only gives us a high-level view. To truly understand how RLDX-1 achieves this, we need to look at the detailed technical breakdown, which we can find in the official GitHub repository.
Absolutely. Let's pull up the GitHub page and really dig into the engineering marvels behind this new model.
Okay, we're on the GitHub page for RLDX-1, and right at the top, it reiterates its purpose: a vision language action model, VLA, for human-like dexterous manipulation. Arjun, what are the specific architectural innovations that make this human-like dexterity possible?
The core innovation here is the Multi-Stream Action Transformer, or MSAT, which expands on existing VLM backbones. It integrates three crucial functional capabilities: motion awareness, long-term memory, and physical sensing, all working together in real time. The MSAT structure is quite elegant. It assigns a dedicated stream for cognition, another for physics, and a third for action. These aren't isolated, they're intricately coupled by joint self-attention, allowing them to cross-reference and learn from each other's inputs simultaneously.
So, motion awareness helps the robot perceive things moving. Is this about understanding speed and direction, not just static positions?
like knowing if a dropped pen is rolling or sliding and how fast.
Exactly. By processing multi-frame observations through a dedicated motion module, RLDX-1 can capture critical temporal dynamics. This allows it to predict object trajectories or assess the momentum of an interaction, which is vital for real-time manipulation. It's not just a snapshot, but a continuous video feed analysis. Then there's long-term memory. A specific memory module is designed to fuse past cognition features with current observations. This helps the robot make history-grounded decisions, going beyond the immediate short multi-frame window, enabling complex sequences of actions and planning.
And the physical sensing component, is that where the dexterity really comes into play? Because that feels like the closest thing to a human sense of touch and force when manipulating objects. It's what prevents us from crushing a fragile item while still holding it securely.
Absolutely. This is where tactile and torque feedback are integrated as a dedicated physics stream. The model is jointly trained to predict future physical signals, meaning it anticipates how its actions will affect contact and force, allowing for extremely fine-tuned adaptive grip and manipulation. This is foundational for true dexterity.
The training methodology is also quite sophisticated, using a three-stage training pipeline. It starts with pre-training for generalization, moves to mid-training for enhancing specific functionalities, and then post-training for task adaptation. Crucially, synthetic data augments rare manipulation scenarios, ensuring robustness even for seldom encountered situations.
It's clear that RLDX-1 is built on a very thoughtful and robust architecture, integrating critical sensory and temporal information. But how does this translate into actual performance on standardized robotic tasks? I'm eager to see the benchmark comparisons.
That's exactly what the next section of the GitHub page provides. Let's scroll down to the benchmark table and see how RLDX-1 stacks up against its predecessors and contemporaries.
Okay, the numbers are in. Arjun, this table shows success rates percentage of RLDX-1 fine-tuned on each benchmark's training set. It's quite extensive, covering a wide array of robotic tasks. What immediately catches your eye here?
What's striking is the consistent superiority across the board. Take Libero Plus, for example. RLDX-1 achieves 86.7%, significantly outperforming the next best, Pi.5, at 86.5%, but also notably higher than GROOT N1.6's 72.6%. This marginal gain is substantial in complex manipulation tasks.
Wow, on some of these, like Libero average and RLDX-1 hits 97.8%. That's incredibly close to perfection. And for simpler Google DM, it's 81.5% compared to GR00T N1.6's 76.1%. This isn't just incremental improvement, it's a decisive lead in many categories, showcasing broad functional capability.
It is. The simpler family benchmarks in particular often involve highly precise insertion and assembly tasks, which directly benefit from RLDX-1's enhanced physical sensing and motion awareness. This consistent outperformance indicates a more robust and adaptable policy.
It's also important to note the diversity of the benchmarks. The first 5 columns cover established benchmarks like Libero and Simpler, but the last 3, Robocasa Kitchen, GR1 Tabletop, and Robocasa 365 are specifically chosen for being long horizon, humanoid, and compositional. This demonstrates RLDX-1's versatility across different task complexities and robot embodiments.
So RLDX-1 performs exceptionally well, but how does it run in the real world? This section on real-time inference is critical.
What did these numbers like 43.7 milliseconds per step on RTX 5090 tell us about practical deployment for builders?
That's an impressive figure, Maya. 43.7 milliseconds per step translates to over 22 hertz. This means the model can make decisions and execute actions more than 22 times per second, which is fast enough for smooth, reactive control in dynamic environments. This speed is achieved through static graph capture and custom fused kernels, essential for low-latency robotics.
For builders looking to adapt RLDX-1, the GitHub provides clear instructions for fine-tuning. You can enable specific functional capabilities like motion awareness or physical sensing via simple flags during training. This modularity allows developers to tailor the model's behavior to their specific robot and task requirements without starting from scratch.
That's fantastic for practical application. It means developers don't have to train the whole model from the ground up to add a new sensor or capability. They can just toggle a flag and fine-tune for what they need.
And for those with memory constraints, the repository supports PEFT LoRa adapters for fine-tuning both the action model and the backbone VLM. This allows for efficient adaptation to new tasks with significantly fewer computational resources, a major win for broader accessibility and deployment on diverse hardware setups.
That's a huge deal for smaller labs or startups. You get the power of a large foundation model without needing an entire data center for every new application. It truly democratizes access to this advanced dexterity.
So, we've seen the impressive architecture, the performance benchmarks, and the practical deployment considerations. But where can builders actually get their hands on these models? This leads us directly to the Hugging Face ecosystem.
Let's explore that, because for a foundation model to truly impact the field, it needs to be accessible, not just powerful. What's available for the community?
We're now on Hugging Face, confirming RLDX-1's accessibility. Arjun, seeing these models readily available here, what does this signify for the development and adoption of Dexterous robotics?
This collection on Hugging Face is crucial. It confirms RLDX-1 as a general-purpose robotics foundation model for dexterous manipulation and its commitment to open science. Providing pre-trained and fine-tuned checkpoints significantly lowers the barrier to entry for researchers and developers. We can see various versions here. The pre-trained video RLDX-1-PT at 6.9 billion parameters, along with mid-trained and fine-tuned models for specific benchmarks like Alex or Robotic. This modularity means developers can pick a model closest to their use case, reducing training time and computational cost.
It's like having a toolkit with specialized wrenches instead of just one universal one. Each checkpoint is optimized for certain tasks, which streamlines development and deployment for specific applications. It's exciting to see these advanced models become so accessible. But when we talk about general-purpose embodied AI, it's not just about capability, it's also about responsibility. Aren't there broader discussions happening around the real-world deployment of such powerful systems?
You're absolutely right, Maya. The potential of RLDX-1 directly connects to ongoing conversations about embodied AI. This brings us to another relevant paper, an insights report from the SAE World Congress 2026, which addresses these very concerns.
Pulling up that report now. Embodied AI in Action. Insights from SAE World Congress 2026 on safety, trust, robotics, and real-world deployment. This abstract clearly outlines the critical challenges that come with systems like RLDX-1 moving into the real world. Arjun, what are the primary concerns being highlighted here?
The report emphasizes new challenges in safety, trust, governance, and operational reliability as embodied AI moves from research to real-world systems like mobile robots and industrial machines. It's about ensuring these highly capable systems can operate dependably and ethically in complex, unpredictable environments.
The paper stresses the need to
treat embodied AI as a systems challenge. This means moving beyond just the AI model itself and considering the entire ecosystem, from the physical hardware to the operating environment and the human interaction. It calls for engineering rigor, life cycle governance, and evolving standards to manage these systems safely.
So it's not just about building the smartest robot, but building a safe, reliable, and trustworthy robot that integrates seamlessly into human environments. That makes perfect sense. A dexterous hand is only useful if it doesn't accidentally cause harm.
Indeed, the report concludes that long-term success will depend not only on advances in AI capability, but equally on safe and trustworthy deployment. This is a crucial takeaway for any builder leveraging models like RLDX-1. The technical prowess must be matched by robust, ethical, and safety frameworks.
That's a powerful reminder that cutting-edge AI is only truly impactful when it's integrated responsibly. RLDX-1 is a huge step forward in capability, but the work doesn't end there.
It's clear RLDX-1 represents a significant leap for dexterous manipulation in robotics. From its innovative architecture to its impressive benchmarks, it's pushing the boundaries of what embodied AI can achieve. And its availability on platforms like Hugging Face ensures it can be used widely.
Yes, RLDX-1 is a key example of how integrating multimodal data and advanced training can yield unprecedented physical interaction capabilities. It's laying the groundwork for truly general-purpose robotic agents in the real world, provided we also tackle the societal and safety aspects proactively.
I'm Maya.
And I'm Arjun.
See you tomorrow.